friends, welcome to video lecture on dynamics of machinery. So under this we'll discuss about Hartnell governor and some numericals. Hartnell governor is the spring-loaded governor. It consists of two bell crank levers pivoted at point OO to the frame. The frame is attached to this spindle so that it can rotate with it. Now, a spring in compression provides the equal amount of force on this roller. Each lever carries the ball at its vertical end and a roller at its horizontal ends. Whatever the force comes on this roller through this collar on the sleeve comes. So it can be adjusted with the help of this nut provided on the top of this spindle by screwing up and down. Let M is the mass of each ball in kilogram. Capital M is the mass of sleeve in the kilogram. R1 and R2 are nothing but the minimum and maximum radius of rotations, R1 and this one R2. Omega 1 and omega 2 is the angular velocity at minimum and maximum radius of rotation in radian per second. S1 and S2 are the spring force exerted on the sleeve at omega 1 and omega 2 in Newton. FC1 and FC2 are nothing but the centrifugal force at omega 1 and omega 2. S is nothing but the stiffness of the spring or the force required to displace the spring by 1 mm. X is the length of the vertical arm. Y is the length of horizontal sleeve arm. R is nothing but the radius of rotation. Now, for the further analysis, consider the single bell crank lever and what are the forces shown here for the maximum and minimum position. So, let H be the compression of the spring when the radius changes from R1 to R2. For minimum position, when the radius changes from this R to R1, the sleeve lift H1 is given by this geometry and this one. So H1 divided by Y equals to A1 divided by this distance, that is X. So A1 is nothing but R minus R1 divided by X. We can get the relation number 1. Similarly, for maximum position, when the radius of rotation changes from this R to R2, the sleeve lift H2 is given by this geometry and this geometry. So H2 divided by this Y equals to A2 divided by this distance X. So A2 is nothing but R2 minus R divided by X will remain as it is. You can get the relation number 2. Now add equation 1 with equation number 2. You can get H1 plus H2 divided by Y towards the left side, and towards the right side here R minus R1 plus R2 minus R divided by X will remain as it is. So this R get cancelled and we can get this relation H1 plus H2 divided by Y equals to R2 minus R1 divided by X, or we know this H1 plus H2 is nothing but H. So H divided by Y equals to R2 minus R1 divided by X. Since here H is nothing but, already discussed here, H is nothing but H1 plus H2. So in the next step we can get H equals to R2 minus R1 into Y divided by X. You can get the relation number 3. Now for further analysis, for the minimum position, for this minimum position, taking the moment of all the forces about this point O and equating the same. So first force with us here, mg plus s1 divided by 2 turns about this point in clockwise direction. This one mg also turns about this point in clockwise direction. This one turns about this point in anti-clockwise direction. So by considering the rotation direction, you can write this relation mg plus s1 by 2 multiplied by this distance y1 equals to fc1 multiplied by this distance minus mg multiplied by this distance. So by doing the further simplification, we can get mg plus s1 equals to 2 by y1 into this term which comes as it is. Again, for the maximum position, taking moment of all the forces about this O point and equating the same for equilibrium of this ball. So we can get mg plus s2 divided by 2. So first force is here mg plus s2 divided by 2 multiplied by the distance y2 equals to fc2 turns about this point in anti-clockwise direction. So fc2 multiplied by this distance plus mg multiplied by this distance with us a2. So you can get this relation mg plus s2 equals to 2 divided by y2 into this term. Now subtract the equation number 4 from this equation number 5 so that you can get the difference between the spring force. That is mg plus s2 minus mg minus s2. So mg get cancelled. We can get s2 minus s1 towards the left side and towards the right side this term minus this term. We know difference between the spring force is nothing but s2 minus s1 equals to h into s, and this relation from equation number 3, h equals to r2 minus r1 into y by x. So you can get from this relation s equals to s2 minus s1 divided by h goes in denominator. So replace the h by this term, that is r2 minus r1 multiplied by x divided by y. Now neglecting the obliquity effect of the arms, that is x1 equals to x2 equals to x and y1 equals to y2 equals to y, and the moment due to the weight of the ball, that is due because of this mg. We have for the minimum position mg plus s1 by 2 multiplied by y equals to fc1 multiplied by x, or you can get mg plus s1 equals to fc1 multiplied by x by y will come here. Similarly, for the maximum position mg plus s2 divided by 2 is the central force with us. We have to take the moment of the central force about this O point. So mg plus s2 by 2, this distance with us, by neglecting this obliquity effect, we can just say y2 is nothing but the y. So mg plus s2 by 2 multiplied by y equals to fc2 multiplied by x. So you can get this relation mg plus s2 equals to 2 into fc2 multiplied by x divided by y will come here. So next equation with us here. Now in this case, the subtracting equation number 6 from equation number 7, we can get s2 minus s1 equals to 2 into fc2 minus fc1 into x divided by y. If you look towards the right side of both the equation, we can get this relation. Now we know that s2 minus s1 is nothing but h into s, and h equals to r2 minus r1 into y divided by x. Simply replace this h term here with this term. Okay, h2 minus s1 divided by h equals to 2 2 into FC2 minus FC1 divided by this one R2 minus R1 into X divided by Y, whole bracket square will come here. Okay, this is nothing but the equation number next. Okay, now here, unless and otherwise the effect of obliquity is mentioned and the moment due to weight of the ball is mentioned, that is neglected here. When the frictional force is taken into account, the weight of the sleeve is replaced by mg plus minus f. Then next one, the centrifugal force at any position, that is intermediate position, by considering the minimum and maximum positions. Okay, for the minimum and intermediate position, you can write S equals to 2 into Fc minus Fc1 divided by R minus R1 into X divided by whole bracket square. Okay, give equation number next for this one. Now for the intermediate position and for the maximum position, we can get this relation 2 into Fc2 minus Fc divided by R2 minus R into X divided by Y, whole bracket square. Now from equation number 9, 10 and 11, the left side is same, so you can equate the right sides. So you can get this relation Fc2 minus Fc1 divided by R2 minus R1 equals to Fc minus Fc1 divided by R minus R1 equals to Fc2 minus Fc divided by R2 minus R. So equating this term with this one and this term with this one, we can get this relation, that is Fc equals to Fc1 plus Fc2 minus Fc1 into this term, and by equating this term with this one, you can get Fc equals to Fc2 minus Fc1 into this bracket, that is R2 minus R divided by R2 minus R1. Now we will move towards a numerical part of this Hartnell governor. Basically, the numericals are related with by neglecting the obliquity effect, then by considering it, by considering as well as friction, then performance characteristics of governor, that is sensitiveness and isochronous. Now we'll move towards a numerical. Let us start first problem on this topic. A Hartnell governor having a central sleeve spring and two right angled bell crank levers moves between 290 rpm and 310 rpm for sleeve lift of 15 mm. The sleeve arms and the ball arms are 80 mm and 120 mm respectively. The levers are pivoted at 120 mm from the governor axis and the mass of each ball is 2.5 kg. The ball arms are parallel to the governor axis at the lowest equilibrium speed. Determine first point loads on the spring at the lowest and the highest equilibrium speed, and second point stiffness of the spring. First of all, write down the given data. So your speed range is given. Okay, so the value for n1 with us 290 rpm, then next one 310 rpm with us, then the lift of the sleeve is given 15 mm, that is h is given 15 mm. Then see the next one, the sleeve arms and the ball arms are 80 mm and 120 mm respectively. Sleeve arms means the value for which one given? Correct, y is given, so y 80 mm given. Okay, y indicate the horizontal distance or the sleeve arm. Then next one, 120 is given related with the ball arm. So vertical distance is nothing but here ball arm can be indicated with the help of this letter small x. Okay, the length for this one is given 120. Next one, the levers are pivoted at 120 mm from the governor axis, means radius of rotation is given. What's about that radius of rotation? 120 mm with us. Then next one, the mass of each ball. The mass of each ball with us 2.5 kilogram. The ball, then the next information with us, the ball arms are parallel to the governor axis at the lowest equilibrium speed. Okay, determine the speed on the spring at the lowest and highest equilibrium speed. Okay, means you have to determine first point, lowest equilibrium speed and highest equilibrium speed. Means you have to find out the corresponding that highest and lowest equilibrium speed. We have to find out the spring force. At lowest and highest speed. Okay, and second point, you have to determine the stiffness of the spring, that is small s. Okay, so first of all, as per information given, draw the lowest position and highest position diagram. Now the sleeve arms and the ball arms, the information regarding this one is given. The lever are pivoted at 120 mm from the governor axis and the mass of each ball is given. The ball arms are parallel to the governor axis at the lowest equilibrium speed. This information with us. So according to this one, first of all, draw the lowest position diagram. Okay, you can draw this lowest position diagram like this. Here is the ball with us. Okay, this indicate the centrifugal force that will act in outward direction. Just give the names at the various spots. We are here the governor axis with us. Once we draw this lower position as well as higher position, you can get the information about the various things given clearly. So this indicate the radius of rotation. What's about this one? The information given about the y 80 mm. This indicate the 80 mm. X is given 120 mm. Okay, then in this case, as the ball arm, this indicate the ball arm, this indicate the sleeve arm. Okay, so information given in the problem, the ball arm is parallel with the axis of governor. So this line will comes vertical, okay, or parallel with this one. Okay, so this information with us. So here the minimum radius of rotation and the radius of rotation of the governor, okay, that becomes equal. Okay, now this indicate the governor axis. Now draw the diagram by considering the highest position. Okay, now in this case the position of the lower arm as well as upper arm will changes. This one acts in downward direction. Here the governor axis with us. This point is nothing but the pivot point. This distance with us 120 mm. Okay, governor axis is here. Indicate FC2. The length for this one remains same, but if you look towards this one, this length with us x2. Now just consider this one as y2. Vertical, this distance now we are assumed as x2, this one as y2, this one and this one will remain same. Now from the pivot point up to governor axis, can get the radius of rotation for that governor, and when the configuration of this governor changes, now from the center of this fly ball up to governor axis, this is nothing but radius 2. Okay, this indicate the diagram for the highest position, and this indicate the diagram drawn here by considering the lowest position like this. Okay, now whatever the central load, by considering the spring force, okay, we can get like this one, mg plus s2 by 2, and here mg plus s1 by 2. Now first of all, just consider this s1 and s2. Let s1 is nothing but the spring load at lowest position, and s2 is nothing but the spring load at highest position. So as per our discussion during the analysis of Hartnell governor, you have to neglect the obliquity effect of arms and weight of the balls. If it is not mentioned in the problem, don't consider it. So by neglecting the obliquity effect of arms, let us get a relation by just neglecting the obliquity effect of the arms and movement due to the weight of the balls we have for the lowest position. Now say in this case, for the lowest position, we have to neglect whatever the movement because of the weight of this ball and obliquity effect, that is this x1. Okay, when x when changes its position. Okay, so here in this case this line is parallel with this line, so x and x1 and y and y1 becomes same. Okay, so you have to take the moment of this fc1 and this one, this force about this point. Okay, and just equate it. The relation can be like this: mg plus s1 by 2, this is about the force, multiplied by perpendicular distance with us s1, sorry, y1 with us, y with us, okay, equals to Fc1 is about the centrifugal force multiplied by distance of the centrifugal force with respect to pivot point. Once again, just see here so that this will clear to you. For the equilibrium of the system, you have to take the moment of this force mg plus s1 by 2 about this point, okay. This moves about this point in clockwise direction, and this one fc1, and okay, if I take the moment of this fc1 about this point, okay, this moves about this point in anti-clockwise direction, okay. So we can get this relation like this one, mg plus s1 by 2 multiplied by y equals to fc1 multiplied by x, by taking moment of both these forces about that pivot point, okay. So in this we can get relation number 1 for the lowest position. Similarly, we can get the relation for the highest position, okay. Now for the highest position, I can get the relation. I'll write here relation first. Now after that I'll show the diagram. So with respect to maximum position, you have to consider fc2, okay, multiplied by x. Now with respect to highest position, just consider here. So you have to take the moment of this force about this point, say the horizontal distance, this is the horizontal distance with us, okay, and you have to take the moment of this force about this point, okay. Now while taking the moment of this fc2 about this one, you need to consider, okay, this distance, okay. So this problem we are solving here by neglecting the effect of obliquity. So this y2 and y become same, and if you look to us here, okay, if the configuration is changes, then at this configuration you have to say this is the distance x2 with us, okay. But while taking the moment, you need to consider the x and x2 is the same, okay. Similarly here y, these terms actually you have to consider as same. Here the fc2, this indicate the fc2, okay, and this indicate the weight of the ball, 2.5 kilogram is given, okay. So fc2 multiplied by this one x2, but as we are neglecting the obliquity effect, you need to consider this x2 as x. So this relation is written like this. Instead of writing here x2, x is considered, and instead of this y2, y is considered. So we can get this relation with the equation number 2 for this. Now for doing the calculations of this s1 and s2, we need the values of this fc1 and fc2. So how can we get the fc1? This fc1 is nothing but the centrifugal force at the minimum speed. So I can get fc1 equals to m into omega 1 square into r1. So what's about this omega 1? Since omega 1 is nothing but 2 pi n1 divided by 60. So in this case we know the value of n1. n1 is given 290. Just substitute here 290 by 60. Simplify this, you can get omega 1 equals to 30.4 radian per second, okay. Now what's about this fc1? Mass of the fall with us 2.5, omega with us 30.4 bracket square multiply by what's about the radius of rotation corresponding to lower position? Yes, how much given? 0.12 is given. Okay, so simplify this, you can get 277 Newton. Similarly, get the value of FC2 and centrifugal force at the maximum speed, that is FC2 equals to m omega 2 square into R2. So what's about the R2? R2 we can get, for that this relation with us, we know height of the governor is nothing but R2 minus R1 into y divided by x. From this relation, after rearranging the terms, what we get here? R2 equals to x divided by y into h plus R1. So what's about the x with us? X with us, how much? X is given 120. Just convert this into meter by this one. Y with us 80 mm, that is 0.8, 0.08. What's about the height of the governor? H. Yes, 0.015. Okay, with us already radius of rotation is given, how much? 120 mm. Just convert that also in meter. So after simplification, what we get? We can get the radius of rotation 0.1425 meter. So once we get the radius, equation number 4 for this one is substituting value of R2 in equation 3. So what do we get? FC2 equals to mass with us 2.5 omega 2. We need the omega 2, just calculate here, since omega 2 equals to 2 pi n2 divided by 60. So what's about the n2 given? 310 is given divided by 60. So what's about the omega 2? Omega 2 with us 32.5 radian per second. Okay, now from relation number 3, substitute the value of omega 2, that is 32.5 bracket square multiply by R2 with us 0.1425. Simplify this for FC2. So what's about the FC2? FC2 we can get here 376 Newton. So once we get the FC1 and FC2, our next task become very easy. Now look towards equation number 1. Here is the equation number 1. Here is the equation number 2. So different terms with us. We know this term. We know this one. We know this. Okay, easily can get the value of S1 and S2. Can substitute the value of FC1 and FC2 in equation number 1 and 2 respectively, and get the value of S1 and S2, that is the spring force at lower position and highest position. So substituting FC1 and FC2 in equation 1 and 2 respectively, and just simplify. Therefore, equation number 1 with us mg plus s1 by 2 into y equals to fc1 multiplied by x. So substitute the different terms and simplify for s1. So what's about this? mg, here the value of m with us 2, so in this problem the value for the central load is not given. Okay, so assume that equals to 0. Okay, so mg plus s1 by 2 means here you have to substitute the value for this one as 0. Okay, this becomes 0. So s1 by 2 multiplied by, just substitute the value of y here, equals to fc1 calculation already done by us. Okay, and x value, this can be simplified like this. S1 by 2 equals to fc1 with us already calculation done by us 277, so multiply by x divided by y, so x with us 0.12 and y with us 0.08. Okay, so simplify this for the s1. So s1 equals to how much we get? 831 Newton. Okay, similarly for the highest position you can get the value for the highest position by substituting. So here is the highest position relations we have written, mg plus s2 by 2 multiplied by y. Okay, so we know the value of fc2. Okay, you have to neglect the value of central mass. Okay, just simplify this relation by substituting the various terms. We can simplify this one like this, mj by 2 plus s1 by 2, here fc2 with us 376 multiply by, so here cannot taken the 2 towards the right side, so 2 will not come here. 376 multiply by x divided by y, means x here 0.12 with us, y with us 0.08. Okay, so here you have to consider the central load as 0. Just consider that value of m equals to 0 and simplify this for the s2, not for s1. Here s2 with us 1128 Newton. Okay, so once we get s1 s2, get the stiffness of spring, that is small s equals to s2 minus s1 divided by h. Okay, so s2 with us 1128 and s1 with us 831 by height with us 15 mm. So all these things we have considered in terms of height we have considered in terms of mm. So you can get the new force or stiffness in terms of Newton per mm. Okay, after simplification you can get 19.8 Newton per mm. Okay, so final answer for the stiffness with us, S equals to 19.8 Newton per mm. Okay, so all the answer right here one by one. Spring force corresponding to lowest position and spring force corresponding to highest position. The lowest position with us 831 Newton, highest position with us 1128 Newton, and spring force with us 19.8 Newton per mm. In the today's lecture, we have discussed about the expression of Hartnell governor and numerical. In the next lecture, we will discuss about more numericals related with this Hartnell governor. Thank you.